Okay, now that we know the configurations and conformations of aliphatic straight chain alkanes and cyclic uh, ring structured alkanes, let's talk about their reactions. Compared to alkenes and alkynes, alkanes are relatively unreactive. They are mostly inert. The reason being the bonds that are found in alkanes, they tend to be very strong. So alkanes tend to be inert. And that said, there are two types of reactions that would still happen with alkanes. So the first one that will happen is halogenation, and the other one is oxidation with oxygen. Okay. The advantage of the alkanes being inert is you can use them for solvents purposes. You can use them as solvents for extraction and purification of products from an organic reaction, because you don't want the solvent to react with your products. So if alkanes are non-reactive, then they're the best. They are one of the best solvents you can use. So like I said, they are inert, but they're gonna be also oxidized or halogenated, like adding halogens like bromine and Cl on them. These are the two common reactions that alkanes will do, even though they are fairly inert. Okay, so for oxidation to occur, you have to take out hydrogens. So oxidation can be defined as removal of hydrogens. It can be defined as increase in oxidation number. Oxidation can also be defined as removal of electrons. That's oxidation. Okay, and the most common one, of course, oxidation is addition of elements of oxygen. So these are the possible physical and chemical definition of oxidation. So hydrogens are going to be removed, or you're adding oxygen element, or you're increasing the oxidation number, or you're removing electrons. Okay, so whenever you're doing oxidation, the reactant that helps you to do the oxidation in itself will be reduced. So you have both reduction and oxidation happening. We call those redox reactions. So one is going to gain electrons and one is going to lose. The one that gains electrons will be reduced. Okay, so let's go with this acronym, oil rig. Oxidation is loss of electrons. Okay, reduction is gain of electrons, oil rig. Okay, and where oxidation and reduction happens in a reaction is called redox. So for the carbon atom, oxidation involves increasing the number of CO or other atoms that are more electronegative than carbon, for example, nitrogen, okay, or sulfur. That's going to be oxidation too. Other than just adding an oxygen, for carbon atom, adding a nitrogen and sulfur will still be termed as oxidation. We'll prove that shortly by doing the calculation of the oxidation number. Increase in oxidation number denotes or implies or shows and defines oxidation. Reduction will be the opposite. There's going to be a decrease in the number of CO bonds, or increase in the number of CH bonds. So if you know how to define oxidation, you will definitely know how to define reduction. It's the opposite, the exact opposite. So now let's determine the oxidation state, or what I call oxidation number. Remember, I said if you're increasing the oxidation number, then what you're doing is oxidizing. So that will be oxidation. If you're decreasing the oxidation number, so what you'll be doing is reduction. The oxidation number will decrease because you're removing, you are adding electrons. Okay, addition of electrons will reduce the oxidation number. So let's do the math. To determine the oxidation number, oxidation state of the carbon atoms, each carbon atom bonded to that carbon that you're looking at will take a value of 0. Each hydrogen takes a value of +1, and then each electronegative atom like oxygen, nitrogen, sulfur will take a count of -1. So let's say you want to determine the oxidation of this carbon. Okay, to determine the oxidation number of unknown central elements like this, okay, we don't know the oxidation number of that element in the middle, the carbon, you're gonna add the number values of the atoms directly bonded to that carbon, or elements directly bonded to that carbon, and then whatever answer you get, you multiply by -1. So negative, the sum of +1 +1 +1 +1. The answer is -4. We do the same thing here. The hydrogen, we said, will have a value of +1. All these hydrogens is +1. The oxygen is an electronegative, an En atom. It takes -1. So again, we're gonna sum these numbers up of the elements directly bonded to the carbon in question, and then multiply by -1. So negative of the answer you get after summing up these numbers, you get -2. So of course, chlorine is another electronegative element we can add on our list. It's gonna take the number -1, hydrogen +1, you sum them up, multiply by -1, you get -2. Same applies here, you're gonna get -2. So which of these carbons is in the most reduced form? The answer is gonna be this carbon because it's mostly negative. The more negative the answer you get, the more reduced the element is. So here the number is -4. And you realize -4 plus +4 gives you 0, and this molecule is neutral, so the charges are cancelling. Same applies here. The carbon is -2. -2 -1, you get -3, which cancels with +3 to get 0 because this molecule is neutral. There's no formal charge. These numbers we are writing here are not formal charges. They're just number values that we use to calculate oxidation numbers. This one is -2 again. -2 -1, you get -3. If you add, that cancelled with +3. Same applies with this one. Okay, so do more practice. Whenever you have a multiple bond, you'll multiply the number value by the number of multiple bonds. But here it doesn't matter, because if you look and see, if you want to determine the oxidation number of this one, you're gonna sum up 0 because carbon cannot steal from itself in terms of electronegativity, so it has a value of 0. So you have 0 on the right, 1 on the left. You add 1 plus 0, get 1, multiply by -1 as always outside the parentheses. So this carbon has an oxidation number of -1. And then what are we looking at? This carbon, you have +1 and a 0 bonded directly to the carbon in question. Multiply by -1, you get -2. Here, this carbon in question, you have 0, 1 plus 1, 1, 1, you get -3 as the answer after multiply by -1. So what is this telling us? The information you are getting here is that alkynes are in their most oxidized form, is the most oxidized form of aliphatic molecules, like hydrocarbons, so to speak, because these are hydrocarbons. So that's an alkyne, that's an alkene, and then this is an alkane. And now you see why alkanes are not reactive also, based on based on oxidation state of the carbon, these alkanes are in their most reduced form. Okay, and the alkynes will be in the most oxidized form as far as comparing alkanes, alkynes, and alkenes goes. So alkanes are inert because, again, of course, this is already in its most reduced form, and it tends to be inert. So, but these alkynes and alkenes are somehow oxidized, and we can reduce them back to -3. So they are reactive. Alkanes and alkynes are reactive. Now, what if you want to determine the oxidation state of the carbon right in the middle? The point is, like I said here, whenever you have multiple bonds, pretend that that element is bonded doubly to the same element. So here you have a double bond. So we'll pretend you have 2 oxygens. On the right, we'll pretend we have 2 oxygens. Now remember, each electronegative element takes -1. So which means on your left you have -2, on your right you have -2. So you sum up -2 and -2, multiply by -1, you're gonna get +4, because -1 multiplied by -4, negative and negative becomes positive. So here you'll pretend again that this carbon in question is doubly bonded to oxygen, so we'll pretend it's singly bonded to 2 oxygens and another oxygen. So we have -1, -1, -1. So you'll add, so up here it's gonna give you -2. Add -2 -1, you get -3, and then you add +1, you're gonna get -2, multiplied by -1, you get +2. The next molecule is similar. So this one is pretending to be bonded to 2 oxygens because of the double bond. -1 -1 gives you -2, and then you have +1 +1. So the oxidation number for that carbon will be -1 times 0, because when you sum these up, you should get a 0. You get 0. And then the list goes on and on and on. So moving from alkynes to alkanes is gonna be reduction. Moving from CO2, carbon dioxide, to methane, that's still gonna be reduction because you're losing oxygens. But when you're going this way, you're gaining oxygen, so it should be oxidation. When you're going this way for alkane and alkynes, you're increasing the oxidation number, so it's oxidation based on the definition of oxidation. So seems like CO2 can be CO2 can be reduced to carboxylic acid, which can be reduced to an aldehyde, which can be reduced to an alcohol, which can be reduced to an alkane. And alkanes are the least reactive. So it stops there, unless you're doing halogenation or unless you're going backwards with oxidation, because alkanes can be oxidized. So alkanes are used as fuel because they can be oxidized as they are burnt up, for example, in your car engine, in form of using gas in form of gasoline and kerosene. You're gonna get some heat, and then that heat generates some energy, which helps in automobile and running engines and all those other applications. The other use, of course, is in cooking. Natural gas, which is a mixture of methane and propane and butanes, can be used to cook, because when you burn it up, you're going to get, as products, you're gonna get CO2, you're going to get H2O, and you're going to get heat when you burn methane in enough oxygen. In enough oxygen, you're gonna get CO2, water, and heat. I hope you remember how to balance chemical equations. So you have 4 hydrogens. Here you have 2 hydrogens, so I'll put 2 here. So you have 4 hydrogens, left, right. And then the oxygen now to the right are 4. 2 oxygens, 4. So I have to put 2 here. So if you have excess oxygen gas, you'll always get CO2, moisture, and you're going to get heat, which is used to cook food. in natural gas applications. Okay. The energy of the hydrocarbon is released when combusted, when the alkane is combusted or burned, and it's going to be used to cook. If the oxygen amount is not enough, here we assume excess oxygen. If it's not enough, then you get carbon monoxide, formaldehyde, and formic acid. Of course, those can be trapped to be used elsewhere. Now, that was oxidation of alkanes, and I've written an example of combustion of methane. So what about halogenation? So besides burning alkanes, you can do what we call substitution reaction, where you swap the hydrogens on the alkane with halogens, which is chlorine, bromine, fluorine, iodine, and all that. But the two applicable halogens that are used to do substitution on alkanes is Br and Cl. Rarely will you use iodide, rarely will you use fluorine in this radical process we're about to look at. So in order to substitute, for example, the 4 hydrogens of methane with, say, 4 bromines, you're gonna need some energy, either UV light or some laser light. And then that should be done in presence of liquid bromine. So if you want to do chlorination 4 times, then you're gonna need, of course, you need 2 equivalents. You're gonna need the same heat energy or UV light. So you can use heat energy. I've used delta to show heat, or UV light. You can use heat. You can use UV light or heat in presence of chlorine to do chlorinations, and then there are 2 of them because you need 4 atoms, so we use 2 equivalents of the chlorine gas because halogens give you the atomic gases. You always get halogens in forms of the atomic molecules. So it has to be a radical process, so we have to break up the halogen molecule. This has to be broken up to give you what we call radicals, and then you use the radicals for the process. So let's talk about that process. So the reaction is substitution because you are swapping the halogen, the hydrogen, for a halogen. X here could be Br2 or Cl2. Rarely will you use I2 and F2. These are the only halogens that will be applied here. And again, like I said, you're gonna need some catalyst as heat or light as a catalyst. Okay, again, it's chlorine and bromine which are commonly used in this substitution reaction. Like I said, I gave you an example of CH4 being converted to CBr4, okay, or CH4 being converted to CCl4 whenever you're using Cl2 or you're using Br2 here. So there's going to be a mechanism for that process. So there are 3 major steps. There's initiation, there's propagation, and termination. So initiation is the starting of the process. This is where you make your first radical. So if you're using chlorine molecule, which is diatomic, so we're going to use fishhook arrows. Remember, the bond is 2 electrons. So move an electron towards one chlorine, move an electron towards the other chlorine. What do you end up with? You end up with 2 chlorine radicals, which is what's shown on here. But this happens because you're providing some sort of energy. Bond breaking is endothermic. You have to add heat to the system. Endothermic, add heat or energy into the system. So you use fishhook arrows because you're moving 1 electron. We don't use double-ended arrow. Okay, you get 2 radicals. That's in the initiation. You made your first radicals. Next, you want to use those radicals for propagation. Propagation is to make more. Okay, so propagation, this is where the halide free radicals react with your hydrocarbon now. removing a hydride to make another radical of the carbon. Okay, and this can repeat as many times as possible. So what we are doing here again is now assume you have CH4, for example. So here I would say probably the R part is CH3 extended to the fourth hydrogen, because that would be CH4. I'm trying to use an exact example here. You know, again, a bond is 2 electrons. So one electron will be given to carbon, the other electron will be given to hydrogen, but because there's a radical close by, that radical will want to accept that electron from hydrogen and make a bond. So that's how you make a bond between the hydrogen that was taken out and the chlorine radical. So you create a new radical. So in our case here, if we started with methane, the radical inside here will be CH3 radical, and then our byproduct will be the HCl. Okay, next, now the newly formed radical will be used to cut apart another chlorine molecule, just like it happened here. Okay, so you will take your radical, combine that single electron with one of the electrons in the bond in chlorine, and the other electron is taken to the other chlorine. So you're making an alkyl chloride, and then you make a new radical of chlorine. So you see, the key feature of propagation is formation of new radicals. The key feature of initiation is formation of the very first radical, which will be used in propagation to make new radicals. Okay, so specifically, I would take my CH3 radical here, which is represented by the R group. Okay, and then create a bond by sharing single electrons, right? This other electron in the bond goes to chlorine. So in my case, my product is going to be CH3, which is now bonded to one of the chlorines. That's an alkyl chloride. Actually, it's methyl chloride. And then you get a radical. Okay. So this is an alkyl chloride. If you are to name it, because you have a chlorine as a substituent, that will be chloro. Okay. So actually, if you are to name this molecule, it's gonna be called chloromethane, or 1-chloromethane. So you've made your alkyl chloride. So you will have swapped this hydrogen that we started with, you're swapping it with the chlorine. That's why we are saying alkanes react with halogens by substitution. You're substituting a hydrogen in the starting material, substituting it with a halogen. Now that was step 2. We've done initiation, we've done propagation. Now how do we terminate? To terminate, you lock up all radicals possible. No more radicals will be seen in the product side. That's a characteristic of termination step. So here, any chloride radicals that are in the system will combine to make a bond. Any alkyl radicals that are in the system will combine to make a bond. So for my case, I'll make ethane out of the methane. Alternatively, your alkyl radical can combine with the halogen radical, and then you make an alkyl chloride, for example, chloromethane, or otherwise generally called alkyl halide. In this case, it's alkyl chloride. If it were Br, it would be alkyl bromide. So generally, this is an alkyl halide. So, and that's how alkanes would react in halogenation. So one can start with 3 hydrogens Then pick up a chlorine from here. Now you end up with 2 chlorines. The hydrogens are replaced. The third hydrogen is replaced. Now you're left with 2. Okay. The byproduct, of course, is HCl. The Cl that was taken out here and the hydrogen that was stolen from here. Through the same mechanism, through initiation, propagation, and termination, you'll get this product. And then it can go one more step where one of the hydrogens will be taken out. Then you get Cl2 becomes Cl3, you're left with 1 hydrogen. And then again one more step until all three hydrogens are replaced. So you get CCl4. These molecules 1, 2, 3, and 4 are all different because they bear different UPAC names, and of course the boiling points are different. The more the electron withdrawing groups you have, the higher the boiling point. Okay. Unless the concentration of chlorine is kept quite low, there is gonna be mixtures. So if you're trying to react this with a little bit excess of chlorine, you'll always get all these mixtures. 1, 2, you'll always get all these mixtures. Where you get mono substitution, di substitution, I say di substitution or dichlorination, or trichlorination or tetrachlorination. So chlorine is not very specific. So if you need a high substituted product, the best element to use is bromine. Okay. Now, but let's discuss how we dictate which will be the main product. For example, if I give you this question and ask you, what will be the major substituted product? What will be the major mono substituted product from this reaction? Let's work with bromine. So I need the major. The question is, what is the major mono? Mono means 1. So you put only 1 bromine. What is the major mono substituted product? From this reaction. So I'm gonna choose a pen here. So the first thing I'll want to do is to notice that these groups are the same. All these metals are the same. So if I put a bromine on either of those, it's just gonna be the same thing. Okay, because all of them are metals. So I would assume we put a bromine there. This will be the product, and we need mono substitution, so I only do it once. I don't put the bromine elsewhere. So again, if I put it on these two, if I leave this as CH3 and put it here, leave this as CH3 and put it here, it's just the same product. So the other option we have is to have the bromine replacing this hydrogen. Okay, and those are the only 2 possible products. So these CH3s will stay as they are, and this time the bromine comes here. So out of these 2, which is the major product? The way to tell is to define the degree of substitution of your radical, because you always form a radical intermediate. Like here, you see, we made a radical intermediate. So the more stable the radical intermediate is, the more reactive it's gonna be. Okay, so in this case you have a secondary radical. You have a tertiary radical because the C radical is bonded to 3 groups. So this is tertiary, not 3rd degree. The tertiary radical is going to be more stable than secondary. The secondary is going to be more stable. This is secondary. 2 carbon containing groups bonded to the carbon. We don't count this hydrogen as a group. So that's secondary. Here you only have 1 carbon containing group, so that's primary. Here there's none. So this is just a methyl radical. Okay. So let's talk about stability. So the more the substituents you have surrounding the C radical, the more stable it's going to be, the lower energy you will have in terms of stability. So you see the tertiary radical has a stability energy of 91. This one has 104. The lower the energy of the molecule, the more stable it is. Now let's look at the bond dissociation energy. How much energy is required to pull out, for example, this hydrogen? You need less energy, 380 kilojoules per mole, to break off this hydrogen to make this intermediate in the propagation step. Here you need 410 to take out, for example, this hydrogen. Let me show you. So to take out this hydrogen to make the radical, it takes a lot of energy. So to make a primary radical, it will take a lot of energy than making a tertiary radical. So that's why I know in this example, this will be the major product. That will be the major, because it must have come from a tertiary radical which bonded with a halogen radical. Okay, this one is a primary. This one must have come from primary, because if you take out one hydrogen, you're gonna make a primary radical, which will look like this. I'm not gonna show the hydrogens. It will look like this. If you take out one of these hydrogens, you get that radical which would have bonded with another radical in termination to get your product. Oh, there's a hydrogen here. To get your product which has a bromine. Okay, which is what you have here. So this is the primary radical which makes this product, and this is a tertiary radical which makes this product. So the tertiary radical gives you the major product, because the alkyl halide formed came from the major radical intermediate. We will continue from here as we finish up the chapter.